Okay, so let's resume. So how many of you have already seen support vector machines? Must have seen. How many, like, what is the highest count of classes anybody has seen support vector machines in? Like 2 classes. Okay, 2 is the highest count. Who else? Who else saw support vector machines? How many classes? Just 1. So 1 class. So he is the highest. Who else has seen the support vector machines more than once? Just 2 classes. Okay. So data mining is fine. What is the other class?
We just talked about it that we can use it in the last few layers if we want.
Oh, okay. 576. Okay. I mean, we didn't really discuss it. Okay. What about you?
There was a statistical software class.
Statistical software. Okay. Okay. Anyway, so did you? Okay, maybe for some of you it's going to be boring, so that's fine. So how many of you have not seen support vector machines and all its gory details? Okay, so everybody has seen the details of support vector machines, extensions, primal formulation, dual formulation.
It's a very high level.
No. Okay, that's fine.
Read all the slides, kind of description.
Okay. So I guess the main point of me dealing with support vector machines is just to introduce a different way of the notion of margins, essentially, or in other words, notion of geometric way of describing errors. Okay, I mean it's a geometric way of describing errors which leads to a certain objective function, which is essentially the same objective function that you've seen several times, but we'll motivate it from a geometric perspective. Okay, and there's going to be some optimization concepts, but we'll skip over one or two of them. But we'll see. Let's move. So support vector machines. So actually, in today's class, we'll not really discuss why they are called support vectors, why there's something called support vectors. But in next class, when we talk about the dual formulation, we'll talk about why they're called support vectors. Okay. So today, just think of it as some model. Machines is just a general word for many of these models. Okay, gradient boosting machines and so on. So machines is not very critical. So SVMs, variations of SVMs exist both for classification and regression. Okay, and but today we're going to only look at the most simplest version. Actually, we're going to look at linear 2-class classification. Okay. So that's what we're going to look at. Although you can make it non-linear using something called the kernel trick. We'll look at it later. And you don't have to do it for 2-class. You can do it for multi-class. Okay, with some ways to do it. But for the core idea, geometric idea, this is good enough. Okay. And for that, let's assume that y is in the set -1 and 1. Okay, which means it's binary, but it's not taking 0 and 1 values. It's taking -1 and 1. We saw this in AdaBoost as well, right? AdaBoost binary classification version. So that's good. And linear. So we're going to actually get a classifier, although we are calling it a different name. It's going to be a linear classifier, which means that we're going to look at a function f of x, which is going to be something like x transpose beta plus beta naught. Okay, I'm explicitly calling out the intercept beta naught. Okay, and the remaining, so you're not actually adding all one's feature into your feature vector, into your feature variables. Okay, so linear because we're going to consider functions like this. Okay, and in fact, since we're going to build a classifier, we'll have a decision boundary, and the decision boundary is going to be determined by this f of x. It's going to be all x such that f of x, which is equal to beta transpose x plus beta naught, is equal to 0. Okay, so this is a decision boundary. Okay, it's linear. In fact, it's a hyperplane. Okay, anything in 1 dimensions, in 2 dimensions, something like this. In 3 dimensions, it's going to be a plane. Okay, this is the equation for a plane. This is the equation for a plane. Okay, this equal to something is equation for a plane. All the points which fall on the plane are determined by this, and hyperplane just means, in higher dimensions. Okay, and so this is the decision boundary. It is a hyperplane. Okay, hyperplane, and our classifier is going to be just a sign of f of x. Okay, so f of x for every feature value is going to evaluate to something, some positive number or some negative number. If it's a positive number, my class is going to be +1. If it's a negative number, it's going to be -1. That's the sign function. Okay, sign of any number is going to be just +1 or -1. Okay, so okay, so we're going to do this in two parts. Okay, in the first part we're going to look at separable data. Okay, it's just a phrase which just means that in this two class classification problem, the two classes separate completely, as in there is no misclassification. Sorry, as in you could find a linear classifier such that all the ones belonging to the positive class, let's say, are on the one side, and all the points belonging to the negative class on the other side. Okay, that's what is meant by separable data. Okay, and then we'll look at then we'll relax this assumption. Okay, as in we can look at general data, general binary classification data. So for the first type, in 2 dimensions, if the data is in 2 dimensions, it could be in higher dimensions, but if it is in 2 dimensions, this is an example hyperplane. In fact, it's just a line, but this is a hyperplane, right? This is actually some beta 1 times x1 plus beta 2 times x2 plus beta naught is equal to 0. Okay. So this is x2, x1. Okay, so this is actually not the hyperplane itself, but this is the hyperplane intersecting that feature plane. So it's just a line. Okay, but the actual hyperplane is the actual hyperplane is coming out of the screen. Okay, that's fine. So if you have separable data, you can find any hyperplane. Okay, so then the question becomes, which hyperplane should I pick? And that's where all the interesting stuff is happening for SVMs. So yeah, so which hyperplane? So which hyperplane to choose is the same type of problem as which model to choose, which minimizes the least square loss, or let's say cross entropy loss. Okay, so we want to, in separable case, there are many hyperplanes which will split the data, not just this line. For example, even this line, split the data, get zero training accuracy actually. So both of these, zero, not training accuracy, but zero misclassification error on the training data. But which hyperplane should we pick? And that's what we're going to decide now. So, and we're going to do that by understanding, by talking about this notion of a geometric margin. Okay. In some other versions of SVM, I guess, lectures, you'll see geometric margin, functional margin, and maybe something else as well. But in our version, we'll just look at geometric margin. Okay. So what is the notion of a margin? Think of the same data. Okay. It looks different, but So margin is basically, if I have this, let's call this, let's say this is the candidate hyperplane, then the margin achieved by this hyperplane is you extend some sort of a region around it. Okay, so try to extend a bunch of region around it. Okay, as in push the hyperplane up and down, basically shake it up and down, as in according to, a hyperplane is characterized by this beta, right? Beta. So beta is some sort of a normal vector, and I'm going to talk about it a little bit more soon. So you kind of have a region around it, and that's going to touch some closest points on both sides. Okay, closest data points on both sides of my training data. Okay, so that width is called the margin. Okay. So actually, in this case, for example, this width here is called or the right way to look at this is, extend it as much as possible. One of the points on one, either the positive class or the negative class will touch that region. That's where you stop. Okay, so it's not like you have unequal sides on both sides. So think of it this way. So this is the hyperplane. You extend it m units this side, m units this side. Maybe here there's a negative point which exactly lies on that boundary. Maybe the positive ones are further away. Doesn't matter. Okay, something like this. Okay, so for each hyperplane there is a margin that I can compute. Okay, wherever it's placed, maybe if it's placed closer to the negative points, then the margin is going to be small. Okay, so our preference from a geometric perspective is going to be get that hyperplane which has a maximum margin. Okay, that's the intuition, that's the core idea. We want to get the hyperplane which has the maximum margin. Okay, okay, so for that, so this English sentence, I mean, we're going to translate it into an optimization problem. Okay, into some symbols. So for that, we need to understand, if I give you a hyperplane, okay, which is a hyperplane is going to be beta transpose x, beta transpose, let's say z plus beta naught is equal to 0. Let's say this is a hyperplane. Okay, this beta is actually normal to the hyperplane. Okay, normal. Okay, what do I mean by that? So this beta naught is like a shifting the hyperplane. Okay, shifting the hyperplane, as in you can set beta naught such that beta transpose z goes through the origin. That's all. So it's just shifting the, there's a plane which is going through the origin, you just shift it by some units. That's like beta naught. Okay, shift. And this beta vector is normal to the hyperplane, which just means that if you pick any point on the hyperplane, its inner product with beta is going to be equal to, in this case, minus b naught. Okay, I mean minus b naught only because it's shifted, otherwise it will be 0. Okay, basically they are perpendicular, so they, wait, what did I say? What is it?
Yeah, it will be beta naught, right? It will perpendicular cos theta inner product.
Yeah, so no, the inner product will be equal to, I'm getting confused. Yeah, what did they say?
It's cos theta, so it's 90, so it will be 0 perpendicular.
Yeah, sorry, it's not, that is true. If it's perpendicular, then that part is 0, then beta naught is not, 0 is not equal to beta naught. So but what did you say? Is that what you wanted to point out? Okay, that's fine. Let me just see what I made a mistake here. Just 1 second. Okay, so actually this I'll get back to this interpretation soon. Okay, so what I wanted to show you was to get this, just tracing back, we wanted to make this into an optimization problem. So let's think of some hyperplane beta transpose, beta transpose, let's say z plus beta naught is equal to 0. Okay, let's say some hyperplane, doesn't matter, forget about the normality interpretation. Now let's say there's a point outside the hyperplane. Okay, it doesn't lie on the hyperplane. Okay, it's on one side or the other. Okay, let's call it point x. Okay, so and let's say there's a point on the hyperplane which is the closest to it. Okay, there's a point on the hyperplane closest to it, let's call it p. Okay, these are all vectors. Okay, just say it's some vector space. Now what I want to find is the distance of this point to this hyperplane. Okay, that's my, I guess, sub goal. I just want to kind of warm up. How far is this point from this hyperplane? Okay, for that I can project this point onto this hyperplane. Okay, and this length here is going to be that distance, let's call it gamma. Okay,
How will you project it? It's like 90-degree angle, so
I mean you have a plane like this, point. What's the projection? So we'll talk about how will you project it. I mean yeah, you can just
angle between plane and the point is perpendicular. So cos 90 would be
angle between the plane and a point.
perpendicular, right?
Yeah. I mean when I project a point, the projected point, the arc or the vector connecting the projected point and this point, and the plane will be 90. Yes, I mean we want it to be 90. Yes, we can have oblique projections as well. Yes, but what is the question?
Projection is basically magnitude into angle between that plane, right?
No, can you repeat?
So projection is nothing but the magnitude multiplied by the cos of angle between that plane and point.
I don't know about that. I'm just saying projection of x on this hyperplane is this p vector. Okay. Okay, so that's fine. So I mean we don't know how to project it. Okay, we don't know how to get this p yet. Okay, but we know that p satisfies the equation of the hyperplane. Okay, so we know that p transpose beta plus beta naught is equal to 0, right? That was the equation. Yeah, right. Now what is this p vector? That we can get okay. We have the same thing here, let's call it x p. So there's a vector here, right? This vector, think of a unit vector times magnitude. The magnitude is going to be gamma, which we care about, the distance. Okay, and this vector, it turns out that that vector is actually equal to whatever, let's call it vector v is equal to gamma times beta vector divided by the norm of beta vector, 2 norm of beta vector. Okay, so beta by norm of beta is just a unit vector. Okay, it's just whatever the magnitude of beta is, just divided by its norm, so it's a unit vector. This vector v, which is connecting these two vectors, okay, x and p, is this vector. Okay, which means that, I mean in other words, I'm just saying that this p vector is just x vector. Actually, if it,
Here, vector v is
let's say this version.
perpendicular to your plane, right?
Wait. So this is the origin. There's a p vector and there's an x vector. So I'm saying that p plus that thing is equal to x. So p plus that thing. So okay, minus gamma times p vector divided by p. Yeah. Now what is your question? I mean, I just have three vectors. I just wrote an equation relating.
According to your first equation, vector v is equal to gamma of vector b and divided by second norm, right?
Yes.
According to that, the direction of vector b and vector v could be same.
Direction of b and v, yes. Beta and v is the same.
They are perpendicular. They are not in the same direction.
Why not?
Vector v is basically the point connecting x and the point on your plane, right?
Yes. Vector v is not the point on the plane. This is the v vector. This is the p vector. If you really want to draw vectors, this is the x vector. I mean, if you know, this is the v vector, x vector and p vector. Whatever. This point is x. Okay. This point is p, and the difference between these two vectors is this v vector. And this is the origin. Okay. Forget about the plane for now. I mean, these are three vectors. It's just a p plus b is equal to x. Okay. P happens to lie on that plane, so therefore P also satisfies that other equation. And because it lies on the plane, the beta of that plane, this is a vector, okay, also determines the v vector. Okay. Is this clear? Any questions? I mean, so right now we are in the subproblem of just understanding how far is a point from a plane, because it's kind of needed for understanding how to define the margin, because we said margin is like a hyperplane, positive negative classes, where how far is the closest point on each class to this hyperplane, right? So we need some sort of a distance of the negative class or the positive class from this plane. So we are just trying to understand what's the distance from of a point from a plane. Okay. Any question? I can put it. I should put it on top. Okay. My mistake. So the distance actually is so the distance is going to be gamma, right? So this is a unit vector. So we can substitute this p in this equation. So it's going to be x minus gamma beta vector. Let's put x there, but times okay, this transpose beta plus beta naught is equal to 0, right? I just substituted the definition of that point. Okay. Which implies x transpose beta plus beta naught is equal to gamma times beta transpose beta divided by norm of beta 2, right? This is nothing but gamma times norm of beta 2, because beta transpose beta is just norm of beta 2 square. Okay, we saw this in the ridge regression thing. Okay, so we got this. What are we trying to actually find is gamma. Okay, so we got x transpose what did we get? X transpose beta plus beta naught is equal to gamma times something. That something, let me write denominator. This is what we got, right? So gamma, we want it to be the distance, whereas the left hand side, it can be positive or negative depending on whether x transpose beta is positive or negative. So actually this is not the distance, but the absolute value of this is the distance. Okay. So this is the distance. Okay, this is the distance of point x from a plane which is given by beta transpose, given by beta transpose z plus beta naught is equal to 0. Okay, so we found the distance of any generic point to any generic plane given by that equation. Now what we'll do is somehow get rid of this magnitude business by saying that for the positive class, when yi is positive plus 1, okay, when yi is plus 1, we can assume that this number is positive, and when yi is minus 1, we can assume that the number is negative. Okay, we can do that. Why is that? If it's the it can only be either it's positive or negative when yi is +1, right? I'm just saying that there's enough degree of freedom that we can say yi times this thing is positive, okay? Otherwise we can just switch, it's not an issue. So yi times x transpose beta plus beta naught divided by norm of beta 2. Now we don't, so there will be some points on, maybe one point or at least one point, because by the definition of margin, which will be on the boundary of the margin, like the region where I elongate, push towards the classes. But all other points will have a distance from this hyperplane greater than gamma, right? Remember this diagram where I said, I think, where was this picture? Yeah, the negative point only, let's say in this case only one point was on the margin, everything else was further away. So all those points are distance gamma, at least gamma further away from this hyperplane, okay? So that's captured by this equation. So basically we want, so this is saying we have separable data, which means that we know that there is a beta for which separates the positive and the negative class. Let's say there are beta and beta naught pair which define the hyperplane. There is a hyperplane which separates the data. Now we know that for any given hyperplane, let's say beta and beta naught, we want to ensure that this margin condition holds for some gamma. So there will be some hyperplanes which are really close to the negative guys, so that the margin is small. Maybe there are some hyperplanes which are far away, equally far away from the positive and negative guys, so maybe the gamma is large, okay? We care about maximizing this gamma, okay? So here's an attempt at an optimization problem, optimization 1, okay? It's gonna be maximize maximize gamma, maximize over beta naught such that yi times x transpose beta plus beta naught divided by norm of beta 2 is greater than gamma, okay? Actually, so gamma is not fixed, so I can also say maximize over gamma, because I don't know what the gamma is, right? So this is an optimization problem. So this is saying literally maximize the margin of those hyperplanes such that they really separate the two guys. So for one, for the positive class, maybe this is, this the left hand side is positive, and negative class, the left hand side is positive because yi is negative and the distance is, not the distance, but this term is negative, okay? So negative times negative is still positive, and positive times positive is still positive, something like that, okay? So this is a first attempt at an optimization problem where we are trying to maximize the margin, okay? As you can see, so then now what we're going to do in the next 2-3 minutes is we're gonna slightly write different versions of the same optimization problem. So we're going to manipulate few things, few symbols from this optimization problem, get to another optimization problem, eventually leading to the SVMs optimization problem, okay, which will interpret then, okay? So what is the first thing we can do is the following observation, that scale, okay? We can deal with scale. What do I mean by that? If I have, I have this data, where is this point? Think of this diagram here. I have this data. If I keep the same hyperplane, which means it's defined by beta and beta naught, it's the same numbers, same beta vector and some intercept. I multiply all my observations by 2, okay, in the sense all my features 2x, 2 times each feature coordinate, 2 times each feature coordinate. Now the points are like further apart, right? The points are further apart because everything got multiplied by 2, except for the line, which is the same equation. I mean, yeah, except for the line, which is the same equation. Even the equation for the line, the x's can be multiplied by 2, so maybe it's in a higher space. But betas are the same, okay? Which means that, but now in this 2x space, the margins look bigger, the margins are like 2x the previous margins. I mean, it's just think of distance, right? Distance, now I've multiplied everything by 2. It's like an enlarged version of the original vector space. So everything is 2x, okay? So there is some scaling issue, and that actually can be resolved by setting gamma is equal to 1 by beta 2, okay? By making the margin the same, if margin is, this is the margin. If margin is higher, then I am reducing the, so I'm tying the margin with the magnitude of the beta. That's all I'm trying to say. Okay. This is basically reducing 1 degree of freedom in this optimization problem. So in this optimization problem, I said let's maximize over hyperplanes. Hyperplane parameters are beta and beta naught anyway. I also said maximize over margin, but I'm saying that this is too much of a freedom because even for because of the scaling issue basically. So we are basically eliminating this gamma. We want to, I mean, in the next step we are trying to eliminate this gamma by saying, I mean, gamma can be anything depending on the scale. So let me take a specific value of gamma, in this case equal to this, and this specific value only because I'm gonna cancel that with the denominator here, okay? So that now the margin becomes invariant to the scaling of the space, or equivalently the scaling of the hyperplane, okay? So what's happening is the optimization problem 2 is maximize over beta and beta naught of 1 by beta. That's the gamma I chose. Or if you're not sure like why I can do this, then just say gamma I don't want to optimize, let me pick it to be 1 by beta, okay? 1 by norm of beta. This times yi of xi transpose beta plus beta naught is greater than or equal to 1, okay? Left hand side was 1 by beta, right hand side had a 1 by beta there, so I just cancel those two out, okay? So this is the second optimization problem. Is this clear? Essentially this is now capturing the notion of margin, in the sense of if the norm of beta is small, then the margin is large, okay? Now, so once we have, we started with the distance from a point, use that to define our initial optimization problem. We set margin equal to a specific choice 1 by beta 2, and we got this optimization problem. And there's one, I guess, simple last trick to do, which is optimization, which is a maximization or something, is I guess hand-wavily equivalent to a minimization of the inverse, okay? So minimization over beta and beta naught of norm of beta subject to yi times xi transpose beta plus beta naught greater than or equal to 1, okay? This is for I is equal to 1 to n, okay? This is for I is equal to 1 to n. The n constraints, you want to have this margin thing to be true for all data points in my data set, right? So this, okay, so I'm going to do two things actually, maximization to minimization. So whatever I was maximizing, I'm flipping that over and saying I'm minimizing the opposite, but I'll also add a square here, okay? So why can I add a square?
Second normal norm would be like,
Yeah, I mean I added a square because it's ultimately SVM formulation has a square, but yeah, I can add a square because norm, it turns out, is like a convex function. So what is it?
Like if you take the minimum of this without square, I think it will come and halt at 0.
No, there is no issue. I mean, you can always you can remove the square. I added a square only because it's convenient for me. Okay. So something, think of that maximum likelihood estimation problem where we said maximizing the likelihood is the same as maximizing the log likelihood. Okay. So that was for the maximization problem. If the likelihood function is, you know, so log transformation is such that it doesn't change the, it of course changes the function value, but it doesn't change where the max happens. Okay, in that maximization problem. Here, minimization problem, you're saying that the square doesn't change where the minimization happens. That's just intuition. I mean, I didn't show it rigorously here. Okay. So that's it. So that's we added a square, and that is essentially the SVM objective or SVM problem for the linear 2-class separable data setting. Okay. So yi's are plus or minus ones, and you're finding the beta, and if you solve this problem, whatever beta and beta naught that you get, that defines a hyperplane. That hyperplane has the maximum margin from the positive and negative classes. Okay. With some, we did two changes from the original. I mean, first of all, we fixed gamma to be equal to 1 by beta. So that actually is the margin. And second thing is we changed this maximization to a minimization problem. Okay. So that's the version for the 2-class separable data. Now, the last part is to extend, as in that step where I said relax the separable assumption. So extend to non-separable data. Okay. For that, what can happen? So what is the extension of the non-separable data? So you have this hyperplane. You have most of the positive guys, as in the positive class, the negative class on the same side, but maybe there's a positive over here and a negative over here. Okay, there's two points that got flipped. Okay, we just want to still have this notion of margin, but now margin, is actually it's not clear how to define the margin because 2 points are flipping onto the other sides, crossing over to the other sides. There is no way to find a linear classifier which will exactly separate, get zero training error, zero misclassification error. Sorry. Okay. So you can't do that. So what you do is you allow for some what is, I guess, colloquially slack. Okay. You're saying, okay, I'm willing to allow for some points to flip over, but most of the points should be I should find a hyperplane such that most of the points are on separate sides. Maybe some points flip over. Ignoring that, I'll still try to maximize the margin. Okay, I still want to maximize the margin. The separation, the plane has to be as far away from positive class and as far away from the negative class as possible. But of course, there's some points which I cannot handle, as in they will mess up with my margin computation. So for them, I'm willing to give some slack. Okay, and that's captured by, in terms of constraint, it's captured by the following inequality. So yi times xi transpose beta plus beta naught. Previously, we were requiring this to be greater than or equal to 1, right, for all points. Maybe there is no beta and beta naught for which this is true. Like the yi times is basically f of x. So y times f of x is strictly greater than 0 for one set of one class and strictly less than 0 for the other class, the f of x. So we can allow for a slack by saying minus xi. Okay, xi. So we are just saying that for some points, hopefully most of the points are for y times f of x. This is actually f of x, f of xi. Y times f of xi is strictly greater than 1, but there could be some points for which y times f of xi could be less than 1. It could be even negative. Okay, which means they are on the other side of the line. Okay, that's the interpretation for this. So this is a slack. So what is this xi? Ci is going to be equal to greater than equal to 0, some positive number which I'm willing to tolerate for some points. Hopefully this Ci is only positive for a few points, for example only for this point, and for all other points Ci is 0. Okay, ideally that's what I want. Okay, how do I ensure that I get that? For that I'll say, okay, I want to minimize for beta and beta naught. That's always the case. I want to find the hyperplane of this inverse of the margin, right? But I want to ensure that not too many Ci's are positive, so I'll just add a constant times sum over I is equal to 1 to n of Ci. Okay, so there's one Ci per point, allowing it to be crossing over the margin, as in like not honoring the margin constraint. But I don't have too much budget for them, in the sense that, if, for example, this coefficient, let's say this thing is 10 to the power 5, really large, so I don't want to allow any, hopefully the Ci's are as small as possible. Okay, something like that. So that's the two class SVM for linear SVM for non-separable data. Okay, this is the and this Ci. So this is I is equal to 1 to n, not just this but this whole equation, and this equation is also I is equal to 1 to n. So these are called 2n constraints. So each inequality there is called a constraint, and there are 2n constraints here, and that is the SVM optimization problem. So why are we looking at the gory details of the optimization problem is that next time we're going to look at how to further manipulate it. So today we just manipulated the objective a little bit and so on to get to these optimization problems. Next time we'll look at a different optimization problem and claim that optimization problem and this optimization problem have the same optimal value and have some sort of equivalent solutions. Okay, and that optimization problem will have different variables, and those are related to what I call support vectors. Okay, but here itself we can notice something, which is that let's say this is the margin here, something. These minus and plus need not be on the margin. Maybe there's a plus here as well, another point. Okay. Okay, so let's take this plus. Let's say there's some minus here. This minus point and this plus point have no influence on the optimization problem here. If I move this minus and plus, a little bit towards in the neighborhood, they have no influence on this optimization problem, because for them Ci anyway can be 0, because I don't need any slack for them. And I mean, by moving the points, I'm just saying I'll change the xi a little bit, xi vector, in this case 2-dimensional, change it a little bit. The inequality doesn't flip. It's not close to the. I mean, this xi is far away such that it's like the function value is far away such that it's not gonna be sensitive to this. It's not gonna influence the optimization problem at all. Okay, so in the sense that this beta and beta naught, the hyperplane, okay, its choice is going to be influenced by points closer to the hyperplane than the points far away. So the points far away are kind of not influential in choosing a beta comma beta naught pair, or basically the hyperplane that I want to pick. Okay, so that's the intuition, and that's the intuition for even support vectors, which we'll probably define next time, where points far away are definitely not going to be support vectors, because they're not really influencing the choice of my hyperplane. The points which are influencing the choice of my hyperplane are essentially called the support vectors. But next time we'll see what the I guess how do they manifest in terms of an optimization problem next time. Okay, and so that's about it for today. So in summary, we looked at bagging random forests just in terms of we are trying to reduce variance. Let's further reduce variance by decorrelating the trees. And next we looked at interpreting random forests, or just tree-based methods, or even nonlinear methods by variable importance and partial dependence plots. Then we looked at a particular way of additively constructing nonlinear models called multivariate adaptive regression splines. And lastly, we looked at the notion of a margin. Okay, notion of a margin as a way to define the objective function. So here, the loss function was completely motivated from a geometric perspective, right? It was not motivated from some sort of a error minimization perspective, like minimize the misclassification error or something like that, right? So So that's the and next time we'll continue and talk about kernel methods and support vector definitions next time. And then we'll get into, so this is pretty much the last nonlinear method. We'll get into unsupervised learning, clustering, and all the exciting things there. So see you.